Introduction to Calculus. To put it simply, calculus describes how quantities such as velocity and mass change. It has two basic procedures opposite to each other. The first one being differentiation. It is about finding the rate of change of a function. The second one is called integration. This is about finding a function given its rate of change, hence making it opposite to differentiation. Both procedures are based on the fundamental concept of limits. This is what makes calculus different to other mathematical topics. But what is a limit? And how does it work under the context of calculus? Let's understand limits a bit more through a simple physics experiment. Imagine in a physics classroom, a student called Tim drops a rock and wants to find its freefall velocity. He asks another student, Jack, to find the velocity of the rock at time equals 1 second. Jack replies, well, we can use the formula y equals to 4.9 t squared, where t means time and the rock started from rest at time equals 0, then falls 4.9 meters after 1 second, so Tim interrupts Jack. This is average velocity, not the exact velocity at 1 second. Jack then says, well, we know after 2 seconds it falls and then 3 seconds. Tim emphasizes, this is again an average. I want to know the exact velocity. How can he help these two students? Well, we can find an approximate answer using average velocity by approaching closer and closer to 1 second. First of all, let's say we find the average velocity over time interval 1 to 1.1 second. Then find the average velocity over interval 1 to 1.01 second. And similarly, over the interval 1 to 1.001 second, hence, we're shrinking the intervals down. Now pause for a second and think about would the intervals shrink down to 1 to 1 second? You can post your answers down at the comment section. Now, what do you notice about these answers? Well, you find the answer approaches 9.8. But why? Well, let us go back to our math classroom and I will explain to you why. Now, recall the freefall velocity formula is just a parabola. Hence, I replaced time t with x for simplicity when I graph the parabola y equals to 4.9 x squared. What we need to do is we need to find the velocity, which is change in distance over change in time. To do that, in this context, we need to first pick a random point P on the parabola. It has coordinates xp and yp. Now let's pick another point Q also on the parabola with coordinates xq and yq. What we're doing now is basically finding the change in y or delta y over change in x or delta x. Refer back to the physics example. This will give us change in distance over change in time, hence velocity. But this is just an average velocity. So what we need to do now is we want to shrink the point Q down to point P so that delta x gets smaller and smaller. So what does it mean mathematically? Well, let me show you. First, let xq minus xp equals to h. This is basically delta x. So that the f of xq minus f of xp would equal to delta y. Hence, the ratio we're calculating, that is delta y over delta x, equals to f of xp plus h, because if you rearrange this equation, xq equals to xp plus h minus f of xp over the interval h. Now, as we shrink point Q down to point P, what we're doing is we're basically shrinking the denominator h to 0. However, this can never be 0 because otherwise we're going to have a division by 0 in this ratio. What does that mean? Well, it means just imagine the point Q is always approaching P, but it will never intersect with point P exactly. It's like a common night dream scenario where you're lost somewhere and cannot find your way home. No matter how many different pathways you tried and how close you are to your home, you just never get to your home. And if you do eventually, that's when the dream is over. Anyway, let's back to mathematics. We want the interval h to be as small as possible, but will never be 0. So this is where the concept of limit kicks into play. What we're saying here is basically we want to take the limit h goes to 0. So we write limit h goes to 0 f of xp plus h minus f of xp over h. Now, this is basically the rate of change of the function f at x equals to xp. Because I've chosen the point P randomly, so I can remove P for simplicity. Now this reduces to limit h goes to 0 f of x plus h minus f of x over h. And this equals to the rate of change of the function f of x, or the derivative of f. I'm using the notation f dash x here. In the future, I'll explain all sorts of different notations we have in derivatives. This is basically the definition of a derivative using limits. And by doing this, taking the limit of the change in y over change in x, essentially what we're doing is called differentiation. Got it? I hope so. However, we're not finished yet. Let's go back to our physics example. Recall the function we have is f of x equals to 4.9 x squared. Let me show you why the exact velocity at time equals to 1 second is 9.8. Put this back to our definition of derivative here. We have f prime x or f dash x equals to limit h to 0 4.9 x plus h squared minus 4.9 x squared over h. Now, let's focus on the numerator. Expand the square in the numerator. We have 4.9 bracket x squared plus h squared plus 2xh. I hope we can all doing this. And expand this a bit more, we're gonna have 4.9x squared plus 4.9h squared plus 4.9 times 2, which is 9.8, x times h minus 4.9x squared. And of course, the quadratic terms cancel each other out. Hence, we're left with f prime x equals to limit h goes to 0, don't forget the limit, 9.8 xh plus 4.9 h squared over h. And because the limit h goes to 0 is never 0, therefore we can divide by h on both the numerator and denominator. Therefore we're left with limit h to 0, 9.8x plus 4.9h. Now, this is the tricky bit, or the most important bit. When we apply the limit h goes to 0, 4.9 times h becomes so small that it is negligible. Therefore, after taking limit, we would have f prime x just equal to 9.8x. Now, this is the beauty of taking limit. After that, we don't have the small interval h anymore, and we only left with one variable x. And this is basically the derivative of the function f equals 4.9x squared. Therefore, when t or time equals to 1 second, so x equals to 1, then we're gonna have f prime 1 equals to 9.8 times 1, which is 9.8. Woohoo! Now, we just proved that the exact velocity at time equals 1 second is 9.8 using calculus. Isn't that great? This should help settle down the arguments between the two students, Tim and Jack, back in the physics classroom. Now, I hope you have a better understanding about calculus, especially differentiation. And I hope you liked the video today. So thanks very much for watching. See you next week.